Welcome back to the first section of Lecture 1, Introduction of AI. We concluded the last video by asking the question of why deep learning has been coined as a term when it's just a subset of machine learning. As we said before, machine learning is suited for analyzing structured data. So, what we mean by structured data is that, simply put, structured data is data that can be organized into a table format, arranged in rows and columns. In other words, it is like an Excel spreadsheet where each column represents a variable and each row represents a record, allowing for straightforward navigation and data management. For example, the revenue breakdown of a company can be formatted into a table where each row could represent a different revenue stream and each column might detail figures for different time periods, like monthly or yearly earnings. This arrangement exemplifies structured data as it allows for easy analysis and manipulation based on rows and columns. And we'll go deeper into structured data later. Traditionally, machine learning has worked well with structured data. It was used for various tasks. The first of these is classification, where we identify which category an object belongs to based on the characteristics of the input dataset. Classification algorithms analyze patterns within the data to assign each data point to a predefined category. Second is regression, in which we aim to predict a continuous value attribute associated with an object. A prime example of this is stock price prediction, where the goal is to discover the best fit line that represents the relationship between independent and dependent variables. Typically, this involves using statistical methods such as linear regression, which is one example of regression, where the algorithm calculates coefficients for the predictive model in a way that minimizes error between the predictive values and the actual data points. Third is clustering, in which we attempt to automatically group together similar objects into sets based on their characteristics. This method involves analyzing the data to identify patterns or similarities that are not explicitly labeled, enabling the algorithm to categorize clusters that share common attributes. To give a practical example from one of the things I've worked on as an astrophysics major in undergrad, I worked with structured data while researching star clusters, which are groups of stars that have formed together. These clusters vary in size and type, typically categorized into two main types: open clusters and globular clusters. These clusters, scattered throughout the galaxy, can be analyzed based on properties such as color and intensity, which indicate how they're distributed across different regions. By applying clustering algorithms, we can group these star clusters based on their spectral characteristics and physical properties, revealing patterns and relationships that might not be apparent from a simple visual inspection. This approach helps astronomers understand the evolutionary history of the galaxy and the life cycle of stars within these clusters. For this analysis, I employed a clustering algorithm known as the Gaussian mixture model to categorize the star clusters into distinct groups. In addition to Gaussian mixture models, other popular clustering algorithms like k-means, spectral clustering, and mean shift are also used. This example shows the effectiveness of machine learning techniques in handling data and extracting insights from structured data. To revisit one of the earlier slides concerning the timeline of AI, machine learning techniques have been employed since the 1980s, including in fields like astrophysics, where they were used as methods for statistical analysis. The prominence of machine learning continued to grow, and by the 2000s and 2010s, deep learning began to experience a significant boom. A notable example of the surge in deep learning is AlphaGo, introduced in 2015, which was designed to master the complex game of Go. Developed by DeepMind, AlphaGo used a combination of machine learning techniques, including deep neural networks and tree search algorithms. It was particularly notable for its ability to learn from large datasets of professional Go games as well as through cell play, a method where it played games against itself to improve its tactics. So, how is deep learning different from machine learning? As we mentioned earlier, deep learning utilizes neural networks, specifically deep neural networks. Unlike machine learning, which excels mostly with structured data, deep learning demonstrates remarkable performance even with structured data. So, you might ask, what are examples of unstructured data? Self-driving cars. Deep learning algorithms process and interpret a myriad of data types, such as the positions of other vehicles, road lane markings, and traffic signals through advanced image recognition techniques. Another example is voice-activated assistants like Siri, which can understand and respond to voice commands. These systems use a branch of artificial intelligence known as natural language processing, or NLP, which is heavily reliant on deep learning. NLP algorithms analyze the structure and nuances of human language by breaking down speech into smaller and manageable segments. So, video and audio data are two examples of unstructured data. So, you might wonder, why are videos considered unstructured data? Unlike structured data, which is highly organized and easily quantifiable, unstructured data does not follow a predefined model or format, making it much more complex to process and analyze. Videos, consisting of continuous frames and varying scenes, represent a prime example of this. Each frame might contain a multitude of elements, different objects, movements, colors, and interactions that are not immediately quantifiable in a simple or uniform way. Humans excel at processing this type of data intuitively because our brains are wired to recognize patterns and contextual nuances quickly. So, take face recognition in videos as an example. If I see my friend A in a video, I can recognize him instantly, even if his appearance has drastically changed. Say, if he's having a rough day and decides to shave his head except for a mohawk. Although I might not be initially surprised, I can still identify him because of my familiarity with his features and expressions over time. Machine learning algorithms may struggle with such face recognition tasks in videos because they rely heavily on detecting and learning from consistent sets of patterns and features. When a person's appearance changes drastically, like shaving their head except for a mohawk, it disrupts these patterns. But even though I know my friend very well, for me to give descriptions in a structured way would be very difficult. For instance, I could provide structured data such as the distance between his eyes being X centimeters, the angle of his nose being Y centimeters, and the width of his lips being Z centimeters, which requires a level of detail that goes beyond casual observation. Similarly, consider the example of a voice file, such as the simple word hello. We could attempt to structure a voice by analyzing factors like pitch and tone, which initially allows us to capture the fundamental acoustic properties of speech. This approach is straightforward when dealing with homogeneous vocal samples, yet it quickly grows in complexity. However, accurately modeling voice becomes complex when we consider additional variables such as gender differences, where men generally have lower tones than women, adding another layer of complexity to the vocal analysis. This variability necessitates advanced algorithms capable of adapting to and learning from the diverse range of vocal tones and patterns encountered in real-world applications. Another factor is dialect variations. Dialect variations present a unique challenge in voice recognition technology. These variations affect pronunciation, intonation, and sometimes even the vocabulary used, making it difficult for standard voice recognition models to accurately interpret spoken input across different regions. For instance, the same word can be pronounced with varying stresses or tones in different dialects, which can lead to misunderstandings or errors in voice-activated systems. To address this, developers must train their models on a diverse set of data samples that represent multiple dialects. This training enables the systems to become more adept at recognizing and understanding the nuances of language as spoken by speakers from different geographical and cultural backgrounds, enhancing the overall accuracy and reliability of voice recognition technologies. So, to summarize the similarities and differences between deep learning and machine learning, they are similar in that both approaches learn from given input. However, it is important to emphasize that deep learning, a subset that involves the use of deep neural networks, enables computers to perform on par with humans in handling unstructured data, such as voice and image recognition. And that is why the term deep learning was coined specifically. So, the defining characteristic of deep learning is a deep neural network. I'll delve deeper into this topic in our next lecture. To provide a brief overview for now, each circle in a neural network diagram represents a neuron or a node. So each of these circles represents a neuron or a node. And these nodes are organized into layers. And when we arrange many such layers, one after another, this structure is what we refer to as a deep neural network. The deep in deep learning refers to the number of layers through which the data is transformed. In describing the history of the development of deep learning, we have to discuss ImageNet. Initiated in 2010, ImageNet Large-Scale Visual Recognition Challenge was born out of the need to push the boundaries of computer vision, particularly in how machines recognize and process vast amounts of visual data more accurately. It was a project funded and organized by researchers at Stanford University, Princeton University, and the University of North Carolina. This challenge evaluates algorithms for object detection and image classification at large scale. This annual competition has had a pivotal role in advancing the field. In the ILSVRC, participants are tasked with developing algorithms for object detection and image classification on a grand scale. So, how grand are we talking about? The dataset used in this challenge contains approximately 14 million images, categorized into 1,000 labels. These labels represent the different objects that can be identified within the images, ranging from everyday items like chairs and tables to more obscure items such as specific breeds of dogs or rare plants. This variety challenges the algorithms to recognize and differentiate a vast array of features and shapes in diverse contexts. The complexity is further enhanced by variations in lighting, angles, and environmental settings within the images, which test the robustness and accuracy of the algorithms in simulating real-world visual understanding. This diversity in the dataset ensures that the algorithms are rigorously tested under varied conditions, enhancing their ability to adapt and perform accurately in real-world scenarios. So, take a look here. The competition has been held annually since 2010. It has been considered as an annual event for programmers to compete with their own algorithms for image recognition. In the initial years of the ImageNet competition, the winning algorithms primarily utilized more traditional learning techniques. Primarily in 2010, the algorithm that won used highly optimized feature extraction methods combined with classifiers such as support vector machines. In 2011, similar approaches continued to dominate, with slight improvements in feature engineering and classifier ensemble techniques, which involved combining the predictions of several machine learning models to improve accuracy. These early competitions showed the effectiveness of traditional machine learning methods, setting a benchmark for the revolutionary deep learning approaches that would soon follow. Looking at the top score per competition based on the top 5 error rate, it used to be between 26 to 28%, which is relatively high, indicating that 3 out of 10 predictions were incorrect. Then, in 2012, a significant shift occurred when AlexNet, employing a deep learning algorithm, won first place. Compared to the nearly 30% top 5 error rate in 2010 and 2011, the performance saw a significant improvement with a 10% decline in errors, down to 16%. This was significant as this was a stark contrast to with a more modest 2% improvement from 2010 to 2011. Having demonstrated this potential, more people started to take notice at this notion of deep learning. After AlexNet's victory in 2012, deep learning rapidly became the dominant trend in the competition, marking the beginning of the deep learning era in algorithms. Then, after a few iterations of deep learning algorithms, in 2015, another milestone was achieved by ResNet, a more advanced deep neural network, which performed better than human capabilities in the same task. Specifically, ResNet achieved a top 5 error rate of just 3.6%, surpassing the human error rate, which is estimated at around 5%. This made ResNet the first deep learning algorithm to outperform human accuracy in such a significant way, setting a new standard for what these technologies can achieve. The competition essentially marked a pivotal moment in 2015 when the algorithms began performing better than humans. To summarize, models used for image recognition initially had a top 5 error rate of around 30%. However, with the advent of deep learning networks, performance improved significantly. Just 3 years later after the introduction of first deep learning algorithm, these models were outperforming human accuracy. So, that's why the industry decided to create a subset of machine learning called deep learning. And deep learning involves using specifically deep neural networks. To clarify, neural networks have been around since the early days of machine learning. However, due to technical difficulties, it was not possible to stack that many layers. One significant barrier was the hardware limitations of the time. Early computers lacked the processing power and memory capacity required to handle the large amounts of data and the complex computation involved in training deep neural networks. Then, in 2012, with AlexNet, researchers overcame these challenges and were able to stack the layers deeply, resulting in unprecedented performance. This breakthrough marked the formal emergence of the field of deep learning, demonstrating its powerful capabilities and setting the stage for its widespread adoption in various applications. In the next video, we'll explore why the 2010s have been considered the era of deep learning, and we'll also discuss the types of artificial intelligence learning methods.